In this class, we've learned a lot about chemical reactions. And so far, we've pretty much assumed that our chemical reactions run until we have all products and no reactants left over. This turns out to not always be the case. Instead, some reactions just run until there's an ideal balance between reactants and products. It's a little like you go to bake cookies and all of your dough isn't used up. At the end, you're left with just some dough and some cookies. That's where a lot of chemical reactions stop. And we call that special point where they stop progressing towards more products equilibrium. So in this lesson, we're going to take a look at what equilibrium is and how we can track a reaction as it proceeds using something called the reaction quotient. Let's learn. Well, let's consider this reaction, which is A plus B going to 2C. There, A and B are reactants, and the product is C. Let's think about what happens to the concentrations of A, B, and C as the reaction runs. Well, let's make a graph, and on the y-axis, we're going to put concentration, or amount of A, B, and C. And on the x-axis, we're going to put time. Now, let's go ahead and mark how much C we have around. At the very beginning, when our reaction starts, we're going to say we have 0 products, which is the normal circumstance. So you have 0, and we start down there at 0 with C. Over time, what's going to happen is C is going to increase, and then at some point it's going to flatten off. The reason it flattens off is because we've made the most products we can. The reaction is basically done at that point. The reason it increases in general is because it's a product, and chemical reactions produce products. Now let's think about what happens for A and B. Let's say A starts there. It's a reactant, so we start with some of it, and over time it drops. So there's our A. The same thing is going to be true of B. So B is going to start somewhere up here. We're going to have some amount of it, and it's going to drop, and it's going to level off at some point. So here you can see that we've tracked A, B, and C over time. And you'll notice that what's happened is our reactant concentration dropped and our product concentration increased. And you can see our reaction is progressing. And what we can do is we can write an expression for our reaction quotient, which is Q. So that's our reaction quotient. And we're going to track the reactants and the products. How are we going to do that? Well, we're going to write products up top, and we're going to raise them to their stoichiometric coefficient. So in this case, we're going to put C up top, and we're going to square it, because there's a stoichiometric coefficient, a big number up front there, of 2 by C. On the bottom, we'll go our reactants, which is A and B. Let's think about what happens to Q. Over time, Q is going to get bigger, because we started out with 0 products, so C was 0 at the very beginning, and then over time, we make some of it. So if I think about my reaction kind of like a racetrack, then Q could kind of mark out like the yard lines on my race. So we would start at 0. That's what Q would be equal to at the very beginning. So that's the start of our race. And then as we progress, Q gets bigger, 10, 20, 30. In this case, we'll say it's a 40-yard dash, so we'll call 40 the finish line. 40 is where we're no longer making more products. So that's actually this same point right here, where C, A, and B have leveled off. They're not changing in concentration, and that means Q wouldn't change. So Q is like the marks on our racetrack. K is a very special point on that racetrack. So our finish line is 40, and that turns out to be the value of K. Just like on a racetrack where every single mark is labeled, so maybe you have the 10-yard and the 20-yard and the 30-yard and the 40-yard all labeled, there's still something special about that 40-yard point, because that's where you're done running the race. And so what we can do here is compare K at a given point in the reaction, and then compare K to Q at a given point in the reaction, and then decide, does it need to run forward or backwards? So for example, let's say we plug a bunch of numbers in for a given set of concentrations for C, A, and B, and we get 20. Well, that would mean that our reaction needs to run forward. We need to make more products. So if we got some value for Q that's less than K, it tells us our reaction's not done yet, and we need to form more products. On the other hand, sometimes reactions can run past that finish line. We can prepare a quantity of C, A, and B that actually has too many C. And if that's the case, when we calculate Q, we'll get something that's bigger than the finish line. So maybe like there. And that would mean we'd need to run backwards towards more reactants. So by comparing Q and K, we can actually come to understand where our reaction is and if it needs to run forwards or backwards. Okay, this is a more mathematically rigorous definition of Q. And notice, just like we did before, we always put products over reactants. So here C and D are our products, and A and B on the bottom, those are our reactants. And they're always raised to their stoichiometric coefficients that we've listed here. We can do Q in terms of concentration. That's the most common way to do that. Or we can do Q in terms of pressure. So here we see it in terms of partial pressures. We'll do a problem using that in a minute, and I think that'll make sense to you. One last note about Q is anytime you have any liquids or solids in your reactions, they're dropped out from your Q expression, and they're actually dropped out from your K expression. So for example, say B was solid, then that would just drop off of Q, and it would drop off of Q over there. Okay, let's actually do a practice problem. These will actually take less time than even introducing the concept. So it says, determine if the following system is at equilibrium. If not, in which direction will the system need to shift to reach equilibrium? So this is asking exactly the question we said Q can answer. We're given a set of reactant concentration and product concentrations here, and we want to know, where are we? Are we at the finish line, or are we past the finish line? Are we before the finish line? So this problem has a few steps. First, we just want to calculate Q. That begins with writing Q. So Q is equal to products over reactants. So our products are SO2 and Cl2. They're raised both to the first power, because that's their stoichiometric coefficients here, 1 and 1, and we divide by our reactant, SO2, Cl2. Notice they're all gases, so we include them all. If they were solids or liquids, we would drop them. Now I'm going to actually plug in the values for Q given. So for SO2, I'm going to plug in 0.05. For Cl2, I'm going to plug in 0.16. And for SO2Cl2, I'm going to plug in 0.12. When I calculate that, Q comes out to be 0.067. So does that mean that our reaction needs to run forwards or backwards? Well, let's think about it once again in terms of our start and finish line. At our start line, we know Q would be 0. At our finish line, we know that Q is 0.078 because that's the value of the equilibrium constant. 0.078. Now we see with 0.67, we're about here. That number is smaller than 0.078. And that means we're going to need to run forward. So the question is it at equilibrium? No, it's not at equilibrium. Well, which direction does it need to run? It needs to make more products. It needs to run forward. Okay, let's do one more. Okay? This one, similarly, gives us a reaction and asks us, is it at equilibrium or not? Notice this time it gives us a Kp, which is an equilibrium constant in terms of pressure, and it gives us partial pressures instead of concentrations. That's no problem. We've already said that Q can be calculated in terms of concentration or pressure. So Q in this case would be equal to the pressure of NH3, that's our product, squared. Remember, it's squared because the stoichiometric coefficient is 2. Divided by the pressure of our reactants, pressure of N2 raised to the first power and pressure of H2 raised to the third power. Great. All right, now let's actually calculate those values. So the pressure of ammonia squared would be 93 squared divided by the pressure of nitrogen to the first power times the pressure of hydrogen to the third power. And when we compute that, we get 0.00128. All right, so 0.00128. Again, thinking about our start and finish line, here our start is 0, and our finish is 4.5 times 10 to the negative 5. Pretty small number. This, by the way, is 1.28 times 10 to the minus 3. So then minus 5 means this has been divided by 10 5 times. This has been divided by 10 3 times. So this is a much bigger number. It's like way out here. And that means that to get to equilibrium, we're going to need to run backwards. So no, it's not at equilibrium. and it needs to run backwards towards our reactants to get to equilibrium. It's overshot the finish line. Thanks for watching this episode of Real Chemistry. Leave any questions you have down below, and you can always subscribe or comment otherwise. Thanks for watching.
Hey, hey.